Okay, the next talk is going to be given by Daryl Schwartz, who's going to address the question of the optimal infrared waveband for surveillance.
Thank you, Dr. Fogger. My name is Daryl Schwartz. I'm an undergrad here at the Center for Imaging Science, and I'm going to, as Dr. Fogger said, talk about infrared surveillance and try to find the optimal band to do so. The outline today will be, I'll give you a little introduction on what the IR bands I'll be looking at, observations I've made, production and analysis, discuss those, draw some conclusions from them, and future directions with this work. So the motivation for my talk, what is the optimal IR band for surveillance? To do that, I needed to find some metrics. For my work, I chose to use the mean square error, peak signal to noise ratio, variance of the image, target detection, and environmental considerations when it comes to design. So infrared detection was first discovered back with Herschel a couple hundred years ago with this thermometer experiment. Back in the 40s, thermal detectors started to become developed and become for scientific use. There's two classes that are commonly used: the photon detectors, which turn incident photons into electrons, and then the thermal detectors, which absorb the photons, taking a thermal change on the sensor and turning that into electronic signal. In the 1990s, there was a big push for focal plane array development for all types of sensors and sizes to collect the IR information. Continually working on the quantum efficiency, responsivity, array size, manufacturability, and increasing the use of applications and where they can be applied in different fields. Like today, I'll be talking about surveillance. And there's a wide variety of sensors right now made of NV, mercury, cadmium telluride, and quantum well infrared photodetectors. So my approach was to compile data from the WASP observations, which I'll explain that a little bit. I used the visible near infrared, mid-wave infrared, and long-wave infrared data from the WASP observations. And then I deduced that data and compared and contrast for seeing clarity, feature detection, and using the aforementioned metrics to decide what would be best for my purpose. And then, as always, there's some visual interpretation with any observations of this type. And then you can investigate the IR environmental limitations, such as with astronomy, your atmosphere conditions, and can grossly affect what you're observing. So WASP is the Wildfire Airborne Sensor Program. We get the data from the Laboratory of Imaging Algorithms and Systems here at RIT upstairs. They model the scenes and I'm taking their scenes to model them as a surveillance scenario. And then from that, I would hope to determine an optimal waveband for surveillance applications. Just give a little information on what WASP uses. They have 3 cameras, short wave, mid wave, and long wave. For my comparisons, I was only concerned with the mid wave and long wave, and not shown here, they also have a visible near IR camera on the system as well. So the WASP observation I was looking at was the Midland Congregation Venture. It's in Midland, Michigan. There's various sources, such as vehicles, transformers, homes, cooling lake, highways, vegetation. And this really provided a variety of thermal observations and discrete objects that I could find. So here's 3 examples from the observations in the visible, mid, and long. 2 observations broken down through the different wavelengths, and you can see visually that there are some differences. Zoomed in, we can get even closer to see certain features are more prominent in some wavebands than others. So the mean square error I used to calculate that is taking the variance from the reference to the actual image. Here I took, what I used as a reference was the visible, because I know what that is, and for surveillance I want to take the IR band and make it look as much like the visible as I can. So just did some programming in IDL to calculate the mean square error, comparing the two, the long wave IR and the mid wave IR to the visible spectrum. And you can see both the long wave and mid wave are pretty close, not a lot of difference. The scale is in decibel, is in DC counts, because I did a lot of the images were post-processed when I got them, so I'm working in digital count units. Peak signal to noise ratio, again, I'm comparing to the visible for both the long wave and the mid wave, and that's just like a noise level system in decibels, where I take the maximum intensity for each image and then divide by the mean square error of it. And again, the long wave and mid wave, there was no clear winner. They were both pretty good. Typically, PSNR is used for image reproduction, and you normally want about 30 decibels, but again, I'm working in long waves, different resolutions, so the fact that it was a little bit lower didn't bother me as much, and it was good to see that both of the wavelengths were correlated together. And then image variance, I just wanted to take the variance through the whole scene, of each scene that I was taking, and we see that both the long wave and the mid wave both significantly drop the variance in DC counts from the original image. Image 2 was actually, a majority of it was a flat field, so we see that if you have a flat field type measurement, the long wave and the mid wave do not suffer as much as with a high density scenes. One calculation I did not get to take, because again I was working with process images with minimum detectable temperature difference. So in order to do this, I kind of made an estimate by correlating the histograms of the two mid-wave and long-wave images, and then compared those to see what was the smallest significant digit count difference between any two adjacent pixels. The mid-wave actually had one digital count on every image, and the long wave was consistent and had 17 digital counts, so it's almost 2 orders of magnitude worse, which means the mid-wave would make a little bit better of being able to detect smaller differences in these types of surveillance. Target detection. One great way for detecting targets is with edge detection. So I applied some edge detection filters on all 3 bands for multiple images. Here's some full views of the scenes. It looks a little messy on some, but you can definitely pick out points of interest depending on what you're targeting. So here's some zoomed in features. The first column, that is actually a bush behind a house, and you can kind of see it in the visible, which is why you can't really make it out. But the mid wave and the long wave, it's the fluorescence from the vegetation showed up. The second column is a car traveling on the highway, and the third is actually a house with a chimney. So you see in the visible, you have the edge of the house, but in the mid wave and the long wave, you can see if it was wintertime when these images were taken, and you can see the heat coming out of the chimney there. So environmental considerations when working with IR imagery. During the day, daylight induces influence on the IR contrast. Atmospheric molecules, as with any observation, can interfere with structured data. And then the surrounding vegetation has a key role in what you see as well. So the solar reflectance influence, for the mid wave, it's about twice as much impact when it comes to contrast. The surfaces around the observation target can experience a contrast of up to 38% with 1 degree C of temperature difference, whereas the longer wavelengths are more stable. Molecular absorptions, as with any observation, we see that they can greatly influence it. And if we look at the long wave IR bands, we see that the biggest contributor to interference would be the ozone, and that's just over a short band, whereas with the 2.5 to 5 of the mid-wave, we're greatly reducing what we can actually see through the atmosphere. And vegetation reflectance, that can be cause some aliasing in your data. The top two is leaves, greens, and leaves, grass, and pine. They're of the green foliage type. The bottom two, beech leaves, rye, grass, and white pine. They're just multicolored. They're showing the fluorescence given off by the vegetation. This is key in IR imaging, as a lot of synthetic materials and the clothing that you wear are made of these materials, and they will reflect and fluoresce just as much as the vegetation will, even after manufacturing. So it's something to keep in mind when, if you want surveillance for safety of your home or for military type applications. So benefits to the thermal array observations is you can go through high density fields. So there's a few programs here at RIT where they'll go searching for forest fires and finding the source of the fires to help out firefighting. You can get through there to find out where it really is. There's a high performance at night. I didn't have the resolution to really show it, but there are plenty of papers and observations out there that'll tell you that. You can actually take individual combination of the bands in series to composite and produce data sets that are most optimal for what you want. And their cost is decreasing a lot because there's no cooling required. They're very reliable, and because of the wavelength that you're looking at, you don't need the resolution on the pixel size, so it allows for better manufacturability and higher yield. So conclusion, what is the optimal IR band for surveillance? With the data I had, I can't conclude that. Both IR bands looked pretty good. But I think I've defined some metrics and some methods in order to move forward into some final works to make a better process of how to determine that. To do that, I would really like to obtain the spectral data. To do that even more, I can do the MDTT and the MRTD, the resolvable temperature difference, to see if there's any correlation with that. I have flying a plane doesn't give you the resolution, you're about half a meter of resolution, so if I could have different focal lengths for various sensor materials, I could figure out both sensor and IR band that would be optimal. Compare single band and multi-band results, and then reduce the original bands that I used into the smaller subsets to see if there's any advantage to that.
Do we have any questions?
So if you go to slide 11 and 12, I was wondering what is the x-axis you have?
Which one?
What do you have on the x-axis? So what are you
Oh, that is samples. I used 7 samples from the data to make the graph.
Oh, do you pick certain spots in the image?
Yeah, I took the data sets from WASP. There was about 400 for each band, so I kind of randomly just chose the same images and then took that data, registered it, and got the same size and registered features so that I was looking at the same thing in the same band as best as I could, because like I said, they were already post-processed.
Can you go to slide 13? Can you explain what is image wavelength?
It's the square, the standard deviation of the whole image. So just going through the whole image, each
So
pixel.
deviation from what? From the mean number of counts? Or
Just
pixels?
the variance of DC count in the image. So it's kind of like it was like a contrast calculation. It was kind of theoretical because, like I said, I didn't have the spectral bands. I couldn't get I didn't have all the information that I thought I would have or wanted. So I was kind of using this as an estimation to see how much contrast I lose by switching to the other bands.
It seems to me that that high variance can also indicate high noise levels.
It could. But I did not take that into account.
So here, do you think that the higher image variance means it is better?
Higher image variance is better in how I calculate this. Because I tried to do it.
It looks like on some other slide you showed the comparison between sensitivity. It was compared to what? Middle infrared to far infrared? No, I mean further. Something. Yes, 1 digital count versus 17.
Yeah, that was just the pixel variation. So that was the resolvable difference. So no two adjacent pixels were lower than 17 digital counts for the long wave. Whereas the mid wave, I could see digital counts of 1.
So the purpose of these instruments is to detect wildfires?
The remote sensing group upstairs, that's one of their objectives. Yeah.
Have we tested them on the images with actual fire on it?
Yeah.
So which one is better to detect fire? Which wavelength?
Professor Vodacek could answer.
Looks like it would be clearly visible in all the wavelengths, even a visible one. No?
There's certain chemical compounds in the vegetation that fluoresce differently. And that's how they can find causes in the fires.
So they can find fire even before it starts?
They might. I don't think they tried that.
You can take a picture of someone holding matches. Just like right at that moment. Fine. I had a couple questions. If you go back to 13.
Okay.
I think this is the same question as what are the axes? So that number 1 there, and then you have 3 dots above it, and that's for the 3 different wave bands.
Yeah.
And so does that correspond to a statistic measured from 3 different images?
Yes. Each 1 through 7 is
Well, let's just talk about 1.
just one.
Okay, there are 3 dots there. Are those 3 different images?
Yes.
There's a visible image, a midwave, and a long wave?
Yeah.
Okay, and then within each image, you're taking the commonly understood variance of all the signal values and all the pixels
Yeah.
for that image. Okay, and then number 2, there are 3 dots.
Yeah.
So those are 3 images. Are those 3 images of the same field as number 1?
They're different fields.
Different field. So this is 7 different fields.
Yes.
Okay. And so it's odd because like number 2, I guess number 2 has low variance in the visible, but the variance in the other 2 wavebands isn't too much different.
Yeah,
for
it
the
was
other fields.
essentially almost a flat field.
Okay.
And there was some expressway, and the expressway seemed to give higher values, which might be why the mid.
Okay.
The mid was more
Right.
responsive to that. It seemed.
Go to slide 10. Is there a shift in X in the lower row?
Yeah.
Between the visible versus the mid and long?
Yeah, I realized that as I was playing the presentation.
Okay.
I was off on that one subset.
Okay. And then on slide 14, the units of MDTD typically would be in Kelvin or Celsius, I guess. And you can't do that because you didn't have the calibration.
Yes.
But you could have the calibration.
If I had the calibration, I could turn those digital counts into some type of
Right.
temperature.
And ultimately, you need that because the digital counts could be more a function of whatever the digitizing electronics were,
Yeah.
unless you know how to map that back to the fundamental physical units then.
Yeah.
Okay, that's all I had. Any other questions?
So it could happen that those 2 different numbers of digital counts actually correspond to similar temperatures?
It could be 1 Kelvin, it could be 10 Kelvin. So I don't know because I didn't have that data.
So it doesn't mean that the temperature difference is 17 times.
No, it doesn't mean it,
Right, so I guess we don't know.
but they don't.
Okay. No more questions? Okay, let's thank Daryl.